Okay, so in this lesson, we're going to talk about the product rule, the quotient rule, and some of the other trig functions we haven't talked about and their derivatives. So the first rule we're going to talk about is the product rule. So if I take the derivative, so D here, notation for derivative, combined with function notation there, is that if I take the derivative of f of x times g of x, and actually I guess it should say d dx, right? That's the notation that should be there. It's actually going to be equivalent to f prime of x times g of x. So the derivative of the first times the second plus g prime of x times f of x. And so we take the derivative of one and multiply by the non-derivative of the other, and then they take the derivative of the other and multiply by the non-derivative of the first one. The order that we multiply these things and add these things is not that important, right? Because multiplication is commutative, addition is commutative. So if you flip-flop the order, it's okay. Let's jump into an example to show how it works. So we have the product of two binomials. So if we kind of view this as f, and this is g, so we're going to kind of get used to this notation of saying f prime g plus g prime f. F prime would be the derivative of the first parentheses, which would be 3 minus 4x times g, which is just the second parentheses, no derivative taken, plus g prime is now the derivative of the second parentheses, which is 0 plus 4, so just 4, and then times f, which is the first parentheses, 3x minus 2x squared. And you could leave your answer like that, but I'm just going to show you some, algebraic manipulation to show you that this actually worked. So if I go ahead and I multiply these two parentheses together, so we have 3 times 5 is 15, and then 3 times 4x is 12x minus 4x times 5x, so that's 12x minus 20x, so that's minus 8x. And then minus 16x squared. And then if I distribute here, we get 12x minus 8x squared. And so if I combine like terms, we get, let me write it in decreasing order of exponents here. We're going to get negative 24x squared. Plus 4x, and then plus 15. So there's our quadratic derivative. But now, let's just say, honestly, a question like this did not have to be done with product. There are going to be some that we have to. You'll see the next one has to. But two polynomials could have been multiplied together at the beginning. So if I go ahead and multiply the original two polynomials together, 3x and 5 is 15x. And then 3x times 4x is 12x squared. And then these two multiplied together is minus 10x squared. And then the last two terms multiplied together would be minus 8x cubed. So if I combine like terms again, here we get 15x plus 2x squared minus 8x cubed. And you can see that if we do the power rule now, we get 15. If I take the derivative now, we get 15 plus 4x minus 24x squared, which is the same thing, just written in a different order. But where we have to use the product rule will be examples that involve trig, examples that might involve radicals. So let's just practice the first one here we have again is with the trig function. So we have 2x cosine x minus 2 sine x. Now, 2x cosine x is the product rule because we have a variable times a trig function. So if I take the derivative, if I do this as f and this is g, so then we have f prime, which is 2, times f prime g, which is 2 times cosine of x, plus g prime f. G prime is negative sine, and f is 2x. All right, so that was only the first part there that we have that I'm going to highlight here, just so you can see that's all I've done the derivative of so far, is just that. And then we have the derivative of negative 2 sine x. Some of you might be thinking, do I have to do the product rule for this? And the case is, if I have a coefficient in front of a trig function, I do not. Do not get thrown off now that we know the product rule, that you have to think that we have to do the product rule here. So the derivative of sine x is cosine x. The derivative of 2 sine x is 2 cosine x. So we have minus 2 cosine x. And you could leave your answer like that. We can combine like terms here. You can see that these cancel. And we end up just getting negative. Usually when we have variables multiplied with the trig function, we write it in front. So negative 2x sine x as our final answer there. Okay. So let's move on to the quotient rule. This one is a little bit trickier because this one involves subtraction and division, which are two operations that are not commutative. So this one is f prime of x, g of x, starting out very similar to the product rule, but now it's minus g prime of x, f of x, all over g of x squared. Another mnemonic device I've heard for this is to refer to the top as the high and the bottom as the low, and call it low d high minus high d low all over the low squared. And d in this low d high d low, the d here is standing for derivative. So when we have low d high, that's saying low times the derivative of the top, and high d low is high times the derivative of the bottom, which is essentially what this notation is. So sine x over x cubed. The low is x cubed, the high is sine x. So low d high. D high is derivative of the top, which is cosine x, minus high d low. High is sine x. D low is 3x squared. Maybe parentheses, not necessarily important, but throw it in there. All over the low squared. Looks kind of messy. We could simplify if we wanted to. Maybe I'll go ahead and do that a little bit here. So you can see that we have top, we have x cubed cosine x minus 3x squared sine x over x to the sixth. Again, you could leave it like that, or you could recognize that up top you have an x squared as a GCF, and really you could just write the top as x squared times x cos x minus 3 sine x. And so now this x squared can reduce with the x to the sixth on the bottom. So our final answer, I guess in simplified form, could be x cosine x minus 3 sine x all over, instead of x to the sixth, if I reduced everything by a power of 2, it is now x to the fourth. Don't get me wrong. The beauty of AP Calculus is that free response questions, you are allowed to leave your answer as a non-simplified expression as such. Annoying part that we have to get used to is that for multiple choice questions, you are probably going to have to simplify to something that might look like this to match one of the 4 multiple choice options. Okay, next one. So if I do low D high minus high D low all over the low squared, let's go for that first here. Low is, maybe I'll write it as a fractional exponent right off the bat. Low is x to the 1/4 times D high. The derivative of the top is 2x plus, minus high D low. Well, the high is x squared plus 2, and these parentheses are kind of important there. Derivative of the bottom, right? It's kind of substantial to rewrite this as a fractional exponent so that I could do the power rule on this 1/4 times x to the negative 3/4. All over the low squared. When I square the denominator, we end up getting x to the 2/4, which is x to the 1/2. Okay, so we could clean this up a little bit. Again, I can combine, multiply some of my exponent terms here. So right here, I could really have that as 2x to the 5/4 minus, I could distribute into the parentheses here and call that a fourth x to the, so negative 3/4. Remember, we, property of exponents there, I'm going to add. So 2 plus negative 3/4 is 5/4. Sorry. Yes. Plus 2 times a fourth is half. X to the negative 3/4 all over x to the 1/2. And I guess lastly, what we could do, we could combine these two terms right here. These are like terms. So I could call that 2 minus 1/4. So that would be 1 3/4 or 7/4 x to the 5/4 plus a half x to the negative 3/4 all over x to the 1/2. And now I could do properties of exponents. I could just divide both of these by a half or subtract a half from each of the exponents and give me a final answer of maybe perhaps 7/4 x to the 3/4 plus a half x to the negative 5/4. And that was just subtracting a half from this and a half from this. So we could call that as our final answer. Now you might have been realizing that we probably didn't actually have to do the quotient rule there. If we go all the way back to the beginning, I could have distributed that division right off the bat and called it x squared over the 4/3 of x. And right at the beginning, that is, if I do think about it as x squared divided by x to the 1/4, so x to the 7/4 plus 2x to the negative 1/4. And now I could just apply the power rule right away, which brings me right to that. One thing I'm realizing now that I have done the power rule here is that I messed up a negative. In fact, I should have distributed this negative, so this should be negative, which means that this should be negative. Which means that this should be negative. So you can see that sometimes using the quotient rule is not necessarily the easiest route. So just like in the last example, this is another good example to look at and say, do not always assume you have to use the quotient rule now that we know it. Okay. In this case, we do not. And it would be very time consuming to try to use the quotient rule on an example like this. In reality, I could rewrite this expression as 9/5 times x to the negative 2. And now I can do the power rule where I multiply the negative 2 with the 9/5 and call it negative 18/5. And now decrease the exponent by 1 and call it negative 18/5 x to the negative 3rd. Or equivalently, negative 18 over 5x cubed, right? Negative exponents could end up on the bottom. So now let's talk about these tricky reciprocal and quotient trig functions. Tangent of x is really sine x over cosine of x, right? So this is d dx of a quotient rule now. So derivative of sine of x over cosine of x, low d high. Low is cosine squared, cosine of x times d high, which would be 0 sine, which is another cosine of x, minus high d low, derivative of the bottom, is a negative sine x, all over low squared, which I could write like this, or I could put the squared on the trig function. Kind of interesting thing that happens here is that cosine times cosine is cosine squared x. Negative sine times negative sine is positive sine squared x, all over cosine squared x. And there it is. You could already hopefully see it, recognize that this is the most popular Pythagorean identity of being 1 over cosine squared, which gives us a final answer of secant squared x. All right, secant x. We are going to have to rewrite this as the derivative of 1 over cosine x. Now there's another rule we could use here called the chain rule. We haven't learned it yet, so I'm still going to do this one using the quotient rule. So low d high, what's the derivative of the top? Well, the top is a constant, so it's d high is times 0, so that just wipes out, minus high, which is 1, times the derivative of the bottom is negative sine x, all over the bottom squared, or low squared, so the derivative is cosine squared. So we have up top, negative 1 times negative sine x is sine x over cosine squared x. And for simplicity's sake, it's actually going to be easier to recognize that this is the same thing as the sine x, 1 over cosine x times sine x over cosine x. It might not seem simple enough, but it's in terms of memorizing these derivatives, because trust me, you will not want to be doing the quotient rule to derive these every time. We're just going to memorize it. So this is really secant x times tangent of x. So we're just going to commit the rest of these to memory. So when I tell you or ask you what's the derivative of the tangent of x, you can just submit this in your memory banks as secant squared x. And then same, if I take the derivative of secant x, we would just say, oh, that's easy. That's just the secant x times tangent x, or secant x tangent x. The cotangent and cosecant can be derived the same way. The easy thing about these ones is they're very similar to the previous ones we just did, except any trig function that starts with a c, and actually it was true for cosine as well, the derivative will be negative. So cotangent's derivative is negative. Instead of secant, it's negative cosecant squared x. And cosecant's derivative is negative. Instead of secant tangent, it is negative cosecant x cotangent x. So now if we ask for the derivative of 3x squared tangent x by using the product rule, we would do derivative of the first is 6x times the second, which is just tangent of x, plus derivative of the second, which is now in our memory banks as secant squared x, times the first, which is 3x squared. Which again, you can leave your answer like that, or usually you will see it written where the algebraic expression is written before the trig function. All right, kind of a long video, but hopefully it explains a lot.